Okay, Xianglin, will you please start?
Yeah, so this paper is called On Decomposing a Deep Neural Network into Modules. And it is, as Dr. Lin said, it is published at FSE, and it is a distinguished paper.
It's 20, right? It's not 22.
21. 20. Okay. And next slide. So it only have 2 authors.
Are there any introductions for them?
No, so basically they are working on DNNs and programming analysis, and they, yeah.
Yeah, this is supposed to be big names. Yeah, let's keep going on. Yeah.
So basically, first we need to know what is decomposition in software development and why it is important. Suppose we have a monolithic software, and we can decompose it into several individual functions. And by decomposing it into several functions, those components can be reused and probably be replaced by other components. And it would be also benefit for the independent testing and independent development. So basically the decomposition is important in software development.
So can you raise a few benefits? So what if we have a decomposed software, and what could be, and what is benefits?
So I think you don't need to like invent the wheel over and over again. When you have some functions available, you can next time you can just reuse it. And yeah, so that's my first understanding of it.
All right, so Yufan, can you raise in some examples why decomposing in software development is beneficial, apart from the reuse beneficial? Yeah, apart from the reuse benefit raised by Xianglin, and what's your point?
Oh, and I think it's easier for testing, because if you decompose it into some functions, then it will be easier to test individual functions than the entire software.
Yeah, and anything else? Yufan, could you raise one more example? Hello, Yufan, are you still there?
Yes, I'm still here, and I think the composition, maybe it will be easier to understand the program and maintain the program.
And in what specific? So Xianglin raised example of reuse and independent testing. And do you have any other examples?
Examples.
Why we want to?
I just think we just write the functions in the programming. So different function will stand for different structure or different ways to do something to solve the problems. So we always write functions and use the functions to solve the problem.
Yeah. So, and Ruofan, what's your point? So, I think Yufan provided very abstract view, saying it's easy to maintain or something like that. So, Ruofan, based on your programming experience, on what do you believe apart from reuse and independent testing, and any benefits from the decomposition?
It's easier for different software developer to cooperate, because different people can be responsible for different components. Then at the end, you just concatenate all the codes together.
Yeah, that's great. Yeah, Changshe, please.
Yeah, I think it's very important technique in engineering that by decomposing those modules, we can easily scale horizontally once we need to deal with a large problem.
Yeah, that's a great insight. And Kushit, you mentioned something in the chat, so maybe you can open your mic, unmute yourself and just speak.
Yeah, I just mentioned that it would be easier to develop because as Urofan mentioned, we can do like as or it's written here in the slides, we can develop independent parts independently, and we just agree the interfaces, and they if we agree the interfaces, they can test it independently, developed independently. I don't know, maintained. I wanted to mention another thing. If you know the such rule called Conway's law, he basically mentioned that the structure of a software team is kind of homomorphic into isomorphic to the structure of the product. So we kind of can organize teams well in that sense too. Because if you have one monolithic software, it would be really difficult for a team to maintain it. So we can organize independent teams.
Yeah, I think both Rolf and Changshe and Kushik and provide very good insight. So from my perspective, it also for the keyword is also for the maintenance. So as long as given a function, however it is small is, if we can clearly define the so-called interface, that means what is input and what is output. Therefore, the other parts, if the other parts want to interact with these modules, we don't care about however complicated the module is, as long as we keep the interface there, and we don't need to care about the whole monolithic software. We just need to focus the small part. And the complication of software development is because the code logic is so complicated, which exceeds the capability of humans or people's mental power. So we have to have a way to split the whole softwares and divide and conquer. So if given a bug, if the bug is relevant to all the aspects of software, it is very, very difficult for us to maintain or even fix the bug. If the bug can be localized into a small module, and this module could be very simple, and as long as this module can put the modularity or the decomposition provide a way that fixing the localized problems is guaranteed that we fix the whole problems. Yeah. Okay, so this is a more abstract view of the decompositions. I think the problem here is that for software assistance, for traditional software assistance, we have object-oriented design, right? We define interface, we define modules. So fixing the bug in modules can be guaranteed that the bug will not happen somewhere else. And if we want to test the modules independently, the modality also allows people to concurrently working on the same projects, right? But for deep learning models, we are training the whole model, which means that if we want to fix a bug of the model, we usually need to totally retrain the whole model. So this leads us to question whether the decomposition of software development can be applied on a deep neural network model. I think that is a key insight, or it is a great question raised in this paper. Yeah, Xianglin, please go on.
So could you please turn to the next?
Okay.
And then when we apply the decomposition in software development to DNN, so currently the state-of-the-art solution might be transfer learning. That means when you have here, for example, you have an English digit data set and you train a model with it. And then next time you wanted to use this model to, for example, classify Japanese digit data set, then you need to freeze the some layers and then retrain the model by transfer learning or fine tuning. But still, it can incur high complexity and low scalability.
So the idea here is that, so you can see the flow here. The flow is saying that decomposition can definitely facilitate reuse, right? So now they come to the question of how can the neurons or layers of neural network models can be reused, or how the models can be largely reused. So the flow here that the paper first tell that what is the status quo for reusing the network. So this is transfer learning, as Xianglin mentioned, right? So given the existing data and existing models, we pre-train it, and so the model can somehow be reused to be further trained on. So this is what aspect of reuse a model, right?
Yeah, this is the current solution. And then, so basically this paper wanted to ask whether if we don't retrain the model, whether we can still decompose it to several modules and then use it.
So the idea is that the paper wants to have a way, so given the trained models, whether we can decompose the model to reduce certain layers.
Not
right,
certain
or
layers, but so here, for example, the first motivated example here is the intro data set reuse. So suppose we train the model with English digits from 0 to 9, and next we wanted to build a sub-problem where we only need to classify between 0 and 1. And then here we ask whether we can reuse the DNN from the previous problem. So basically, it wanted to decompose this DNN into 10 modules, and for each modules, it can classify 1 digit. So basically, it's one this all problem, something like that. Yeah.
Yeah, so that means we have based on your description, we have a very complicated model, but we want to decompose it to simple function, right? So we have a function, we have models to classify 0 to 9, and now we want to a smaller or simpler model, which only be able to classify 0 and 1.
Yeah, so
right.
the output, we only have 2 output. One is, suppose we wanted to classify 0, then one output is the probability of this digit being 0, and the other output should be the probability that this digit.
Oh, so basically it's 0 not, right? 1 or not, 0 not.
Whether or not, yeah.
Yeah, 2 or
so
not.
we can decompose this DNN into 10 modules, and each module have 2 outputs. Is one output is that digit.
Yes or no question.
Yeah, yes or no question. So how to do that? We would introduce the approach in later. This is the motivating example.
Okay, so here the motivating example is more like extract a sub problem from a complicated problem, right?
Yeah.
It can be considered reuse, but what if I just raised a question? So suppose we have a model from 0 to 9, right? And what if I want to train the models which can classify 0 to 20? Right. So
yeah,
that part of it.
So probably you should have modules that can classify whether that. So here we only consider digits.
Yes.
It's 20. So basically you have a modules that can help you to classify whether it's 20 or not.
Yeah, but anyway, so this is an actual image, right? 0, 1, 2, 3, 4, 5, 9. It is after all, it is image.
It's image.
Right. So we could make the images to be more complicated than 10, right? 10 is still an image, 11 is still an image. So it is still feasible to extend the model capability like this, right? So
how they do that is you would output a probability. Suppose you wanted to classify it 0 with 20, and then one module would output the probability of that number being 0, and the other module would output the probability of that number being 20, and then you compare the 2 probability and select the higher score one. That's how they do it.
Yeah, but the problem, so I think the more interesting question is how to retrain the model, right? So if we retrain a binary model.
No. Here we don't retrain at all in the approach part.
So basically they have a way to slice a few neurons or layers to reuse them for the new model, right?
They are deleting some edges.
All right. So more like a prompt. More like a prompt here, but it's not Yeah, but it is because when we once have a work, we just submitted recently. We talk about suppose we have a data set from 0 to 9, and we find that several training examples have been predicted incorrectly. We want to know whether we can localize a few individual layers, and only retraining the individual layers can guarantee that the whole model the problem can be fixed by the whole model. So this is more like a localized modularity that, but this sounds to me more like a problem.
Correct.
Okay, let's keep going on.
Yeah, the next one. So the next reuse problem is like what you said, we merged, maybe not, we merged two problems. So suppose we have a DNN trained with English digits and the other DNN trained with English letters. And then we wanted to classify, for example, between 0 and A. Then we can reuse the modules.
Why not we just run the example to each model individually and get the results? Why do you combine them?
So the modules is the weight of the module is much less.
So could you clarify the task? So the original task is very clear. Given the digital images, we recognize the digit. Given the letter images, we recognize letter. But what is the composition task? The composition task is
the current solution. The input might be from 0 to 9 and some English digits.
And we want to clarify them.
Yeah.
And what if we feed these images, or given images can be either digit or letter? We feed these images into two models individually or respectively, and we just choose the result. Isn't it the same? Why do we need to combine them?
So I think the module itself is lighter than the whole model.
Lighter. So that means the combined model.
Weight is.
You mean that if we maintain two models too heavy, we need to have a way to combine these two models.
I think the reason is that you need to normalize the softmax probability.
Yeah.
So you cannot just fit it into each of the model and get two softmax probability. Then you don't know whether it's a digit or a character.
But
let's check. So I just need to check. So I don't know what is the consequence if we feed the digit model with the letter. So what's going to happen? If there's something weird happens, we can somehow it's kind of exceptional. So we just look into the normal signals, right? Suppose given we feed a digital, suppose we feed a digit into a digital model, and we're given a softmax or have a logics which is maybe 0, have 1, 0.9, and the rest is very small. But we're feeding a letter into a digital model, and we find that there's very weird softmax. We can say that. I don't know, but yeah. So here the rule of thumb mentioned that if we need to have a way to integrate the softmax or the logics, right? Okay.
And then next slide. Next slide is about the scenario of replacement. So here the setting is that when you suppose you train the DNN models A and it performs worse on digit 5, and you only wanted to replace the faulty part, and you might have a DNN model B which can perform better on 5, and you can replace the modules of 5 from A to B. So it will be much easier. Otherwise, the current solution solution. I'm not sure what they mean by the current solution. I think we don't have.
Yeah, so I still have a counter argument that as long as the model A output the prediction of 5, we just ignore it. And so we have many ways to combine the model, right? So if we just we want to combine the output of 2 models, we have a lot of ways to do this. And why bother to do this in the internal layer perspective?
It didn't involve any retraining. So
Okay, so if it is not involved in retraining, does it also need to slice a few modules and recombine? Do they do something like that?
by the weight, basically set some weights to 0 and do some. So later we will introduce the techniques.
Okay, so here maybe we recap with the problems. The first problem is that we want to slice or simplify the model, so which means that we can reduce existing neurons and the layers. And the second problem is that suppose we want to combine 2 models, we want to have a way to reuse existing models. And the third one is that we want to replace one feature or one sub-functions of one of models by the others. Right. So, and I think for the third scenarios, I didn't see the applications. I mean the real world applications and why and how often do we really need to think about these cases? But for the first one, I think it is possible because when it comes to a model, or sometimes the pre-trained model is too large for a customized application. So definitely we have these scenarios. And for the third ones, maybe we want to have more classes, right? We want to have a model. We want our model to have more to support more classes. So that is also a real world applications or seemingly practical applications. But for the third one, I just feel it is a little bit imaginary. I don't see the application scenarios. And anyone else think about how practical or how real this problem is, the problem of replacement?
Whether it looks like this, for example, there is a non-specific DM what works specifically. I mean, Olin works very well for 5, but other parts maybe not. For their methods, they can only, for example, generate the weight from this DM model, then use this kind of module to be combined with the model A, but no need to retrain model A or model B.
So this, yeah, I understand this is an example of digital, right? So, but in real world cases,
so I mean, there are 10 class, 10 classification problem, but only, for example, only one of it have the best result. I will choose 5 from here, and another one maybe for 1, choose 1 from here. Another one maybe choose 3 from here. Then it will.
Yeah. So that the case. So that means one model is good at predicting 5, like model B, and the other model is good at predicting any digits except 5, right?
Yeah. Yeah.
So we want to combine this. If that's the case, why we just do some integrating? For example, if the digital model predicted it is a number, not 5, for A, we know that when A predict 5, it is not accurate. So which means that as long as predict 5, we don't believe it. We just turn to the result of B. But for model B, unless it predict 5, we will not believe the model and we turn the result to A. So it's still a very simple heuristic to combine output. And why we need to combine the model. Here we're talking about we have a need to have a new model.
But the things is just as you mentioned, you need to 1 by 1. For example, if the model A says 5 is good, then we believe that. If not, we need to choose B. But for it,
Yeah.
for their method, no need. They will only use the entire, their build model or modules. Then they can definitely quickly got the prediction. I think this is an advantage.
But from user's perspective, they have no, because fix is not fundamentally improve either A or B, right?
Yeah.
So we just want to have integrations to take the advantages of each individual models. So if we have a simple solutions, why we bother to take a more risky, right? Because we always want to manipulate the neurons. It's more like a surgery. But if we just combine the results, it's supposed to be a more, at least for me, it seems more confident and more safe.
But
I don't know. Maybe they have a better way to decompose. To decompose. So here, they do not retrain, which means that they have to manipulate the weights and the neurons a little bit, right? I'm not sure. I didn't look into the approach. Xianglin have the final say, or have the authority to say what the approach really is actually designed. But if I'm the one to look into this example of maybe replacement, kind of module replacement, it's more like a bagging approach, right? We get outputs of each individual model, and we know that which model has advantages in which predictions. So we just need to synthesize an output or have some rules on output, and that'll be easier and simple. And if a simple one can do his job, and why we resort to a more complicated solution? And especially we want to manipulate the neurons, which introduce some risk. Yeah, I just raised a question here. I'm not familiar with, maybe they have very reliable technique, underlying technique. Yeah, but the overall idea is that given the numerical model, and how do we reuse part of the neurons and layers to facilitate some maintenance task? Okay, so let's keep going on.
Yeah. So next we will introduce the approach. This is the overview of their approach. So they will first, through concern identification, and by concern we mean different labels. Suppose we have a DNA that can classify digits from 0 to 2, and then the first step would do this concern identification and then separate the DNA into 3 modules. And then the next step would do this tangling identification. That means you identify some edges that contributed to the non-dominant concerns. And then the last step is
so what is so TI means what? The tangling identification.
So the first step is to identify edges that related to the dominant concern. The next step is to identify the non-dominant concern. And this by this you can build this 1-vis or classifier, right? And then
so here I may raise the question: what is dominant and what is non-dominant? What is the definition of dominating and non-domination?
If we wanted to identify the concern 0, then the non-dominant concern would be 1 and 2.
I see.
And then the last step is to CM is the is the concern modularization. They would they would perform some, I'm not sure how to say this. Basically, they turn this into a lighter weight module.
So here, this is the input module, right? And this is the output module, right? Oh, this is input model. And this is an output module. Or the output module or model.
module, because here you see it has two outputs. One is 0 and the other output is non-zero. So it would have three modules.
I see. I see. So this is output. So actually, this is more like a slice of the whole network, right? And
so this is the overview.
In terms of overview, so here I have a question for tangling. So for this tangling, which means that whether some edges is shared by all the concern, which is called tangling. So this somehow means the edges were inevitable. We have to count.
By looking at their algorithm, personally, I think so. In the first step, they add the edges that contributed to the dominant concern, and then at the second step, the tangling identification, they would input some non-dominant class examples, and then adding those edges that contributed to this non-dominant concern.
And why would you do that? As long as we have these concerns, that's okay. Right?
Otherwise, you only have one output. You don't know. It has no function at all. You need to have two outputs. One is to say yes, and the other one say
no. So which means that we want to identify the additional links which can contribute to no, the answer of no.
Yeah, correct.
Okay, so yeah, I have no questions on these slides. Anyone have a question on this overview? I think this overview is kind of important to understand the follow-up slides.
But I need to mention that they only consider this fully connected there.
Yeah, I think it's pretty
Well, it's one of the components.
This may not be a very realistic application. Okay, so anyone have a question for these slides? Yeah, I think you should attack as hard as possible, because this is for discussion. If we would just want to know the content of the paper, we would rather to read the paper. But since every people here, we organize discussions, I think we can raise questions and express our concerns as much as possible. Okay, please.
Yeah, earlier I just noticed that this kind of looks a recent research paper. They learned, or they kind of offered a new kind of thing called active dendrites.
What?
Yep. Go ahead.
So which one? Kushit, what's your point?
So they introduced the thing called active dendrites to avoid, they said, to avoid catastrophic forgetting. The thing is, just by looking at the input, they turn off some of the nodes in the neural network. So for that reason, they can train the same network to do different kind of tasks, right? And for example, they were using one robot hand to open the cupboard or move the things, and let's say it was playing like 10 games by only training once. So yeah, this kind of looks like a decomposition, because it's different weights of the neural network is learning different things, and they're also training again. And if you look at their diagrams, this kind of looks like the same as this, because because
I think the direction is the opposite. So they want to put as many functions as possible into one model. And here, the question is that assuming that we have already have the model which can do many things. The many things here means that it can classify 0 to 2. And here we want to derive a smaller model, maybe the module, which allow us to just to classify 0 or not, 1 or not, and 2 or not, and what is the technical solution. I think the question is here. But anyway, I think there's something similar. They do share something similar. But overall, I think the technique here Yeah, let's move on to see more technical design in the follow.
Mm.
Mm.
So for the concern identification, yeah, the goal is to identify edges or weights that contribute to a single concern. And how did they do this? So here, suppose we wanted to decompose it into a module that can classify whether it's 0 or not. First, they would input some examples from 0 class, and then iterate through each layer. If some neurons is 0 or less than 0, that would delete all the edges connected to that neurons. So here, the black one, you can see the black one should be less than 0. So it would delete those black edges.
Less than 0 means that there is no signal from the neuron, right?
Yeah, so basically the weight
Mhm.
is not important. The neuron is not activated.
And
then-
I have a question. The signal, if the signal is 0, whether the 0 is really not useful?
Because they the assumption is the network using ReLU activation, and if it's less than 0, then basically all the weights connected to that neuron is useless.
Yes, I do understand there's no output from there's no contribution from that neurons, but whether no contribution. Here, what is definition of no contribution, right? So if it is yeah, but the 0 signal, the 0 signal is still kind of signal, right?
No, then that means you can think that for the next layer, all the weights would times 0. Then
I think it's not time 0. I think there's an item which has been set to 0.
why?
So here we just asking.
It's fully connected layer, so it's basically weight times inputs plus some bias. And
yes, which means that one coefficient is 0. Which means that one coefficient is 0, right? Because because you can see this neuron output 0, which means that on all the maybe just like this weight output 0, which means all the weights relevant to this neuron is 0, which means the corresponding item is 0. And that's all. And
you say that the neuron is 0. It might
the output of neuron is 0. So I understand you correctly. You're saying that we want to identify a single neuron, and if this neuron
is 0,
output 0, I think the neuron is not 0.
Oh yeah,
the output of the neuron is 0, right? And then this neuron will have no contribution to the prediction of certain class. I just have expressed a bit concern about this definition of contribution, because sometimes the neuron output 0, it still have some side effects or consequence for the final prediction. So suppose
in their case, if you can think if x becomes 0, then no matter what value the weight is, then
okay, maybe
the output
maybe let's accept the assumption. So the neuron output 0 here. I think the more accurate statement is that for all the images or given concern detection class, for all the instances or samples under these classes, if one neurons will always output 0, which means that this neuron have 0 contribution for the prediction of the concern, right? So let's assume that, let's accept this assumption first. So in this case, we can have we can remove a lot of neurons, which always output 0, right?
So
So
in
we remove neurons. Basically,
remove,
if we
remove the edges. The edges.
Remove edges, but whether we don't also the neuron, the nodes, right? So we deleting one node means deleting a set of the edges, the incoming and outcoming edges.
And in their case, the even the assumption, they just select some examples, and for each example, if some neuron output 0, then they just eliminate the edges. So it's still questionable, this approach.
Whatever it is, it actually just remove a few neurons so that it can have a stable network. And this stable network is called concern.
Yeah, in practice, they would just set the weight to be 0.
Yeah, I understand.
Yeah, here I just want to say their paper is not that well written because there are some errors. Like here, the I, it's not I, it's I plus 1, and here.
Where?
Oh, it's here. Oh, the first box. So they say xi is equal to xi times wi, but it should be xi times wi plus 1. Otherwise, it's just not make sense. And then the next one, the wijk, right? The if condition. So every j and k inside this box should swap their position. So it's wikj. And then the next box, it should be bij. So the k should be j. But anyway, it's very confusing.
Yeah, so I think it is not a very good practice to provide an algorithm papers over,
and
say over 20, maybe over. I think the algorithms will be as small as small possible. So this is too long.
I checked their code. They basically translate the Python code into this pseudo code. Yeah, like line.
Which means that best paper sometimes requires luck, right?
Yeah, and
so I think this is a very different angle.
What does K and J means here? What does K and J means here?
So let me think about it. The J means the J's concern J, and I need to draw a graph maybe. So it's very detailed. Like if your input is, we have so consider the simplest condition where we have one example. It has d dimension, like for example 3. Then the W matrix should be 3 by. Suppose we have 2 output class. So this is the output. We have 2. Then it's this is the weight, right? And this is the not D. Sorry. Never mind. It's the input, and then this is the output layer. And here they are updating the common edges. That means we have 3 neurons here, and the output is 2. We have 2 neurons, and then this weight should be W. So this 1 1 1 2 2 1 3 1. 2, 2, 3, 2. So this is where this edge is 1, 1. This is 1, 2. So they have a for loop to check if this neuron is less than so if the weight is less than 0, then they delete some edges, something like that. So they have some loop condition to do this. So they will first check all the incoming edges and set them to 0, and then check all the outcoming edges and set them to 0. If you can check the details.
So you think the position of JK is not correct?
Yeah. Otherwise, you look at it. K is equal to the length of the first dimension, right? So K should lie in the first dimension and J in the second dimension.
Oh, but actually, I think the notation is correct, because when we represent the weight metric, we usually put the output layer dimension first, and then the last dimension last. Yeah.
But
so I don't think it's wrong. I think it's correct.
But K should be the length of the first dimension.
I think the first dimension should be the output dimension.
The first dimension is the first dimension is here.
Do you see some notation that you put the output dimension first and
I
input
think
dimension second?
it's correct here. It's following the standard.
But anyway, even if this is correct, I think the format is a little bit
yeah,
it's too long a format. And also my question is here. You have the third point, stop when age is smaller than 10% of all ages. So is that a must? So we just talk about we want to delete the neurons which output 0, right? Always output 0. So whether there's a number that we want to remove, right? So here you're saying that stop here. You say stop when age is smaller than 10% of neurons.
Yeah. So
sorry, the ages. So why we need to set such a size? We have to do that. So this is that a stop condition?
So that is correspond to the 18th line. They have an indicator. If all the weight of the model is less than 0.1 times the original edges number, they think the model will be too sparse. So the 0.1 is just an empirical stopping sign.
And what is the stop condition? So
here, the 18th line, if the indicator is true, then they won't.
And what is the indicator?
Indicator is set. So if all the edges is less than, so if this condition is satisfied, then the indicator will be true. The indicator is the input.
And what if the indicator is true?
So you can see that they no change to edge if the indicator is set. So they won't change the weight. So here the W and capital B is the original weight and bias, and the B and small b is the updated or the module. So if the indicator is true, they just set. They won't make any changes. All right.
So I think here, I think the abstract view here is that we want to have a way, and the output signal, right? The output signal is supposed to be the clue for us to delete the certain neurons. right? So can you pinpoint which statement in algorithms is way to delete the neuron or delete the edge?
Here the 25 line. So they set Dijk to be 0. That is equal to delete the edges. Because you can see that this edge, if the value is set to 0, then it's equivalent to eliminate it. So all in line that assign the value 0 to the DI is deleting the edge.
Okay, so can you explain maybe the third box? So it's called updated output layer edges.
I'm not sure why they explicitly write this. This is, I think it's equivalent to line 21 to 28, except here they doing this for the final layer, the output layer. Oh, I know, because for 21 to 29, they would check the incoming edges and outgoing edges, and for the final layer, they don't have any outgoing edges. So they just write it again here.
So here, what is the maximum?
Where?
I mean the Dijk equals max, etc., etc. So what does this max mean?
Sorry, can you, which
The
line?
max, 24, the max.
If it's less than 0, then
Yeah, maybe we go to
that's
details.
basically is setting it to 0, right? Because Dij might be 0, and if the Wi is less than 0, then it's 0. So they want that.
But which means that if it's smaller than zeros, then it takes a larger value between Di and Wi.
Yeah.
And Di could be something positive. Could Di be something positive,
No,
or Di will always be
I don't
negative?
think so, because the initial value of Di is Wi, and I think so.
I see. So which means which means always be smaller, right?
Yeah, correct. So you can see that from, for example, from line 10 to 16, they are setting the value of Di to 0. So that's the only operation here.
Okay.
Yeah.
Okay, so I think we have enough talk here. I think the takeaway here is that it will just keep checking whether certain neurons will always be 0 or negative in order when we prediction certain concern, or when we're predicting certain zeros, 1 or 2, etc. If the neurons will always output the negative numbers or 0 numbers, it will be removed. So the sliced or the smaller network supposed to be a network or module, of certain concern. Okay, let's keep moving on.
Can I ask a question? So they use all the training data set whose level is 0 to check whether they are, for example, a neuron, whether their output is 0 or negative.
Maybe.
Yes, you're right. I think the answer is
Yeah.
yes.
I don't think they use the full data set.
I think it's supposed to be the data set of certain concern, right?
The certain
Right.
concern, but I'm not sure, because they set a stopping condition, and you don't need to iterate all the input, then it might already come to this. I'm not sure.
I did similar experiments before. But I use all the training data whose level is 0. Then I find that actually the neuron that can be removed is very not that much.
Oh, okay.
That's why I
So if you go through all the training data sets, so because all the neurons will be activated I think the majority of the neurons will be activated 1:1, right? So
Yeah.
as long as one neuron is activated, it cannot be removed. But if we just using a part, suppose we have 50K data set, and we just use maybe 5K, maybe these 5K is under the label of 1. So the rest on 45K is not used. So these 5K images or samples can only activate a very limited, maybe a limited number of neurons. And so the rest of neurons was supposed to be removed. I think that is a general idea of this concern identification. Okay, let's keep move on. Yeah.
And then the second part is tangling identification. They propose several different tangling identification methods. That is TI imbalance, TI punish negative examples, TI. I forget what S means, but we can explain them one by one. So could you go to the next slide?
Okay, so maybe I have a reminder here. The goal of tangling identification is going to find, because here the idea that we know that all the neurons and ages are relevant to 0, but what if the neurons and ages which allow us to predict something else, right? So somehow, if I understand it correctly, they want to provide a network which is an abstraction for all the rest. If the consent is 0, we want to have a way to abstract 1 to 9, right? So we want to add a few ages on the consent 0, so that we're able to predict all the non-zero digits.
Yeah.
Okay.
Yeah. The next one. Oh, wait, sorry.
No, this is the animation you want to create.
So sorry. Yeah. The next one. The first method is called TI imbalanced. That means an imbalance is introduced while adding examples from the positive and negative labels. So basically, again, suppose we wanted to separate the module that can classify digit 0, then first, the input from 0 class is used, and then apply the CI. And then the next step is to add non-dominant inputs with 10 with 1 ratio. That means if we have 10 positive labels, we would feed in 1 negative labels. So this is
positive means dominating.
Dominant. Dominant. And negative means non-dominant concerns. Yeah. So this is the imbalance, and then the adding edges part is similar.
You're just going to see which, when we having, for example, we have 5K 0 data, we just feed into 500 non-zero data. So we can see what additional neurons will be activated. So we add them back.
Yeah, correct. I think there are some details in the algorithm itself, but I didn't check the details then. But the idea is to add non-dominant inputs with imbalance ratio.
And how about the output ages? Okay, so it haven't go to output ages, right?
Output.
Yeah,
what
so
do you mean?
which means 0 and non-zero. So which they finally will have a way to merge 1 and 2.
It's just a demonstration, but like here, I think if they should input 20 positive labels and then 1 negative labels from class 1 and 1 from 2, then it's relevant to these 2 classes.
So let's see the details later.
No details.
Then there's no details, right? So you have already provided abstraction.
If you are interested in algorithm yourself, please check the paper. They have 5 detailed algorithms inside the paper. And then the next method is called punish negative examples. So this time we have this time the ratio become 1:1, but it just means we let positive labels update first and then the negative labels. I know the previous example.
What's the difference? So I don't see the difference of 10:1 and 1:1.
I know that they follow this format, but they are two different techniques. One is that the positive label.
And what do you mean by update? So as long as if I understand correctly, we only preserve the activated neurons, right? What does the update means? So it's more relevant to this algorithm, right? So it's more relevant to these algorithms. Just depends on how to. So, but is that really matters? Some neurons need to update first, or some neurons need to update later.
Yeah, it matters from the experiment.
For the algorithms, right?
And then the next approach is higher priority to negative example. So this time we add the non-dominant inputs first and update the network, and then we input the dominant.
Yeah, I think this is not. I'm not sure whether it is very strong opinion, but I think the algorithms need to design so that the order does not matter. Right, the algorithm needs to design. So the here is that we want to. I think from a high level point of view, we just want to know which neurons are activated for the concern 0, and which neurons are activated for a sample neuron, a sample concerns, or sample a non-dominant concern, right? That is all. So whether we want to look into the dominating first or non-dominating first, it doesn't really matter. The algorithm is supposed to provide such a property. The order does not matter. As long as we select our interested data samples, and all the neurons supposed to be from whatever 1:1 or 10:1, and the kept or the removed neurons supposed to be the same. So that is just from my basic idea. Okay, so by the way, is there any questions up until now? I hope that we're not discussing too details. Just feel free to ask any question.
But here I'm confused because I copy a sentence from the paper. They said update dominant concern first and then non-dominant concern. But from the graph and the title, the higher priority to negative example, I think they meant they add the dominant inputs first. It's just, I don't know.
You mean the non-dominant concerns first?
Yeah, because the title and the graph suggest that they add the non-dominant input.
Yeah.
But
okay,
the
okay, point. Yeah. So it seems that this paper have a lot of I don't know, the typos or mistakes, etc. So let's keep moving on. Yeah, because we haven't got some expected exciting stuff. So they're just want to have a way to prone the ages. So that's all, right?
And then the last technique is called strong negative examples. That means, so still here we update the positive labels first and then negative labels later. But this time they only add strong edges from the non-dominant inputs. That means if the
yeah, so how do you define the strengths? What do you mean by strong or weak?
I think they report some empirical value, like if the value of the weight is above that threshold, they would add it. And
you consider strong, okay?
Yeah, that's the definition. And then we come to the concern module.
Sorry, can I ask a question? When does this 5, I'm not sure, is 5? I mean, the
4 or 5, yeah.
5. Are they all used, or they will choose the best one?
Oh, they all used, I guess. They all used.
These 4 techniques, you mean?
Yeah.
I think they do
For
some like ablation study in the
yeah.
experiment and show which one performs the best. But
Oh,
I think they provide very
for them, they will only use one every time. Then they will say maybe one of them perform best.
yeah.
I think there does not have baseline. Right? This approach cannot have baseline.
Yeah, correct.
So they can only have a linear study. So they try different rearrangements of the ages
yeah.
to. Okay.
And then this is the concern modularization. So this is the process of separating the parts of monolithic models belonging to us. Personally, I'm not sure whether this part really matters, but could you go to the next slide? I would introduce how they do this. This is the CM channeling, in short CMC. That means for each layer, they will select those non-dominant concern edges and compute the mean, and then assign it to the first neuron, and then set all the other edges to 0.
So sorry. So
You get
yeah, I don't get it. So for now we have. So I think let me talk. Let me talk my understanding. So idea is that we already have the neuron here. We try to merge 1 and 2, right? So this is like
correct.
Right. So here, how do we merge 1 and 2 into a non-zero function? So the idea is that select a non-dominant.
So that means, so like here, those 3 edges are connected to the negative neuron, and then they will.
So they just takes the average and connect it to a new.
Yeah, they built this neuron.
Oh, I think definitely I understand this is SC people what SC people do. EA people will never do that, I guess.
I just I don't understand, but this is what they do by channeling. So they would do this to each layer.
Yeah. So anyway, their way of the aggregation, they do need to aggregate 1 and 2 into a non-zero, but they just using the average and differential abstractions too straightforward, and they really have some concern on this technical design. Yeah, let's keep going. Yeah.
And then
It's only output layer or area layer.
No, just auto layer. There's no need for
the channeling is each layer.
Each layers.
And then can you go to the next slide? The remove irrelevant edges. This is this is for the last layer.
This is for the last layer, right? So why they want to merge? Maybe you can keep going on. I understand this way of merge and aggregation, but I cannot imagine why we need to do this on the non-output layer.
Non-output, but from the algorithm, because I checked the algorithm, the channeling part, they have still a loop condition, and the loop is
it's for layers.
They iterate each layer. So and then this remove irrelevant edges. This is done to the last hidden layer. But basically, I think they are doing the same thing. So they would be.
So I'm trying to interpret. So here we giving the concern we have a dominant.
I understand now. So before in a previous example, slides, they would compute the mean and compute the abstraction, and then here, the difference is that suppose we are doing this to module 1, then 0 and 2 should be useless. They will set. They will. Sorry.
So it seems more to me. You can I try to interpret it. So this the result, right? We just look at the result. This result is between 0 and non-zero. The result here is 1 and non-1. Right. So
The graph,
your iteration or your loop is loop across layers or loop across the output.
but they saying that they will first remove the irrelevant edges or incident edges and then do the channel.
Yeah, you can see if their animations mean something, we will find that all the non-output layers is keep intact, right?
Oh.
There's nothing changes,
Yeah.
right? So unless we find there's the output layers, there's something not useful. Sorry. So what
So
these black neurons means,
is
and
you
why do we need to remove this neuron?
I don't know. I don't know. But basically, I know what they mean by this graph. They remove the irrelevant edges because this is module 1, right? So they remove the edges that link to 0 and 2.
But
I
if we
don't
want to merge 0 and 2, these black neurons still need to be preserved. All right. So and here you can see this one, the first node and the third node, both of them link to 0 and 2, but the first one is preserved and the third one is has been removed. It need to be removed. And yeah, I just get very confused just based on their.
and for the words, I mean, those description in their paper, inside the remove irrelevant edges, they mention about if the dominant concern is not 0, then they will set the first neurons to like not 1 or not 2. But if the concern is 0, they will set the second neuron into not.
I think there's more details. So I think we need to skip this.
I know, but
think-
they only explain these details in.
Yeah. Anyway, so here I need to take a stop discussion here. Overall here, yeah. So after they got concerned, they will have some additional or some noise edges. So the goal of the CM channeling is about aggregation, right? So we have a more concise neurons here.
Yeah.
Okay, that's all they have. If that's all they have, then how this technique relevant to the problems we discussed before? So we have not only we have slice or simplification, we also have composition and replacement, right? So this is a interdata reuse, and you mean that the approach can be applied on all these approach? Is that generalizable? And how they are generalizable?
Because for all those 3 motivating example, you only need to decompose the DNA into some modules and then put them together. For the first problem, they just.
No, so the point is that as long as 0 and non-0, 1 and
As you
non-1.
can decompose them, then.
Yes, I got the point. So here, let me rephrase. So as long as we can separate the concern of each network, so we can, even for we have 0 to 9 and A to J, and we have 0 non-0, 1 non-1, A non-1, non-A, and J non-J, right? So for each individual nodes, we will have their, so more like we decompose a full network into maybe a multiple classification problem into several binary classification problems based on these concern slicing, etc. And that's all, right?
Correct.
How this got best paper? I didn't understand.
And their paper, the writing, really, I need to complain about the writing. It's so confusing.
And personally, I don't believe it's called modularity. And how we call modules is basically concerned. It's just basically a transform. I think let alone, so we still need experiment results and need some theoretical proof that their slicing is really relevant to really reliable to turn to transform a multiple classification problem into a binary classification problem. Later on, we'll technically sound. But how this can be called as modules? Maybe each concept called a module. I think this concept is very different. Yeah. Okay.
But they don't have theoretical
Of course, yeah, I do understand this is not theoretical part, but
and it's only fully connected layer.
okay.
Anyway, let's go to experiment.
Okay.
They use 4 data sets: English data set, M-MNIST, and then F-MNIST, and then K-MNIST, which is Japanese digital,
Japanese.
and English.
E-MNIST. There are so many MNIST. So maybe we can use more data in our future work. Okay.
And then the model part, they consider 1 to 4 hidden layers, and each layer contains 49 neurons. So basically, they have 4 times 4, that's 16 models. And the research question, the first question is, how efficient are the decomposed model? But by the evaluation, I think
they talk about effectiveness instead of efficiency, right?
Oh, no, I think they talk. Oh yeah, they talk about effectiveness, not efficiency. Because they didn't talk about the time needed to decompose them. And then the second experiment is, does it enable reuse? And then the third question is, does this enable replacement? Yeah, and then next step. So basically,
so they just compare
the
before and after decomposition, right?
Yeah, so the first line is the model accuracy, it's the original accuracy. And then you have TII, TIPN, yeah, they compare different techniques. Right? And the accuracy means the decomposed accuracy, and the JI means Jacquard similarity between different modules.
What do you mean by different modules?
So the
Jacquard index, which means the similarity between 2 sets, right?
Yeah. So
what is a 2 sets to be good comparison?
So you take 2 modules, and then put all weights from one module into a set, and then the other one as a set, and then compute the Jacquard similarity. And this JI should be the mean.
What it really means, or what is the indication?
It wanted to measure the similarity between different modules. I think that means by this
And you know why we need to do this?
They didn't explain it very well.
Yeah, so
but from the experiment result, you will find that the TIHP, which means the higher priority to negative example, we update the negative examples first. It achieved the lowest Jacquard similarity.
So somehow you mean these 2 measurements is correlated. And you can see this one is very low, right? The TIPN and TIHP is very, very low. The TII and the TISN is somehow reliable.
Yeah, the conclusion is the TISNE is the best. Some accuracy even surpassed the original.
And we can see there's some. Yeah. Okay, so it seems that. Okay, let's move on. So, any questions on these slides?
Did the author mention why they only include, for example, MNIST 1 to 4? Why not?
The MNIST 1 means the MNIST data set with 1 hidden layer model, and then MNIST data set with 2 hidden layer model. So the 1, 2, 3, 4 means the hidden layer, and the data set just. Oh, that's what they mean by 16.
Okay. Okay, let's move on.
And then the next research question is that modularity enable reuse. So first we compare the intra-data set reuse. That means we have a model that classify English digits, and then we build this sub-problem.
All right.
Yeah, and basically means this means F means this.
Yes, and there's combinations of about 0 bases. Okay.
And then
this is also another 2 combinations, right? So they try all the combinations. So you have 4 data sets, right? They see what 2 is actually 6, right? They try every pair of combination.
And then the next one is the inter data set. That means they take English digit 0 and Japanese digit 0, so from 2 different models. And here we have 100 scenario.
I see. So
here the result is.
So they'll try different models. Right?
Yeah. Can you see the top conclusion? The intra data here. The intra data set replacement loss about 0.5% accuracy, where the inter data set replacement loss like 5.
And how this inter data can have a replacement? I think replacement
the inter data set is that they built a new model with same model architecture, and then train, for example, using the English 0 digit and retrain the model. And this
we can read this. That's okay. So that's their experiment. And now let's come to the limitation.
Yeah,
by the way, I think we have finished all the experiment. Is there any questions?
They didn't measure for example, there are 10 classes. They didn't measure once, for example, the accuracy, I mean, their modules for 0 performance. How about the performance? The comparison between the performance of the module 0 with the module 9, for example.
That is the intra data set comparison. Can you go to the next, previous slide? This one. This is the intra data set. So you have 10 class. That means you have 45 scenario, right?
Yeah. So,
right? You pick.
Okay, I just have a concern after the. Okay, I just feel, because I also did such experiments, I didn't find much gains from the. So I'm wondering how they claim their method.
Improve, right? So but improve is very marginal.
Yeah.
It can only have 0.03%
average
improvement. So it's basically
and
very
average.
marginal.
Average. That means they still have some scenarios where the modules is worse.
Yeah, but I checked before. In my experiments, maybe around 50%. I mean, for example, there are 10 classes. At most, 5 of them will perform better than original one. At most. So I just wonder how this paper, how the authors claim their method, why this is important or something like this.
I don't
Yeah.
good luck.
Yeah, because last time I didn't use so complex, I mean, method. I just use simple one, and I also obtained the similar results. Then we say, oh, it is no worse. Then let's forget this.
Yeah, you can see someone go this direction, have the publication on this paper.
Yeah, I just wonder how they claim why it is.
Yeah, but the problem is that even if you get the best paper, when we digest and have discussions, it will not have a very high remark. This approach very hard to receive. But anyway, I think this is the angle, the presentation of perspective, very good. So, but let's keep going on. So
The
yeah.
limitation is given by me.
Okay, this is your
Yeah, I think
right?
they did not report the time complexity and
Mm.
the network seems.
Which means that if you are the reviewer, you try to reject it.
Yeah, I will try. And they only work on fully connected layer. It's not scalable. Again, the writing. I think the writing.
Yeah, we can see the best paper is very very limited. So sometimes need some luck, right?
Yeah, and then the conclusion. Let's see the conclusion. So they claim that the decomposed modules are significantly different and performs the same or better. The difference should be given by the Jacquard similarity. And the second and third statement claiming that reuse and replacement is possible, but it could incur some accuracy loss.
All right. So any comments on this work? So just feel free to comment on this paper.
Oh, by the way, I checked their code. I think the organization of their code seems quite good.
So writing is good. So the
code
implementation is good.
Oh.
And but the writing is so you're criticizing the professor. Okay. So any comments on this work? After all, this is the best paper. Oh, it's a distinguished.
May I ask how they say their application? I mean, why it is module reuse is so important? I think it's problems. I mean, concern is why it is important, why replacement is important, and because yeah, it's possible, but they have some accuracy loss. Why we need this?
I feel that they just because decomposition is for reuse and replacement, so they have this scenario. But I didn't see.
Yeah, I think Xianglin is very hard to argue for. Xianglin is trying to reject their paper, so it's very hard for Xianglin to defend for their approach.
Yeah,
I guess.
Yeah, I just feel that we missed the
distinction.
Yeah. Okay.
Probably
So
remember our proposal. We mentioned the results.
It is not me to kill your best paper, David. Okay, so my comment is here. So if we look in this paper as the year of 2022, we do have a lot of concerns because SE people, I think not just SE people, I think a lot of the people in non-AI areas have equipped enough knowledge to understand the neural network model. But if we look into the time of 2020, so there is information gap between the AI people, the software engineering researchers and the AI researchers, and the expertise of them is not that strong. So a lot of ideas seems to be novel, but when we look into this one, we just feel conservative. I'm really conservative to say this is a very good paper and how practical this approach is going to be, right? So which means that in our future research, we need to keep up with the times. So if there's new technique coming, I don't know. In the future, maybe 10 years ago, it's Android development, right? So when the Google is pushing the open source Android applications, the one who joined it, the researchers working on the Android applications, so they will receive a lot of awards. But then this comes to the AI, right? So the neural models, even very simple approach, and have I think it's more like the parallel ideas. So traditional software requires modularity, and so AI still requires sensing. It sounds good, but you can see if they look into their approach, they just transform a a multiple classification problem into a binary classification problem. That's all. So they believe that the binary classifications is a compositional component which help to reduce. It is logically correct, but whether we will do this in the future. So this
No.
Yeah, that is very big questions. So in the future now, I think maybe 3 years ago, smart contract is something big, right? By blockchain, something very new. And now it's supposed to quantum computing, right? In the future, autonomous driving, something. So as long as we have a chance to keep the time, the work, there's no need to be very excellent. Work no need to be very high quality, I guess. So as long as it is new as normal, we have a chance to get acceptance. If we really get lucky, and we might even get the best fit. So that is basically my gut feelings. All right, so I think that's all what we have for today's group meeting, right? Yeah, we have only one paper presentation. I encourage all of us to ask as many questions as possible. I think this paper, maybe it's very hard for us to digest some technical contributions because we already have better understanding. That's why we always ask to report the latest works instead of the old works, because the latest works have a stand on the shoulder of the giants. But one thing we take away, not just from the technical perspective, but from the topic selection, how do we design a topic? I think the new topics and the multidisciplinary topics from the emerging area, I think that might be the way to go. Yeah. Okay, that's all what I have for today's presentations. Is there any other questions? If there's no questions, let's call it a day. Thanks everyone for the attendance.